Hi, this video completes our coverage of the plain binary search tree, meaning the binary search tree that doesn't do any self-balancing. We've presented a bunch of operations on the tree. Now we're going to analyze those and work out the asymptotic efficiency of each operation, meaning the big O runtime of each operation. First, let me preview where we're going to end up. This video is going to derive all of these and tell you where they come from, but the summary is that the constructor that creates an empty binary search tree takes constant time. All of the other operations take big O of h time. H is the height of the tree, and in our plain unbalanced binary search tree, the height could be as much as big O of n. So all of these other operations take linear time. Those other operations are contains key, so given a key, determine Boolean true or false whether the key is in the tree or not. Find key is given a key and returns the pair that contains that key or throws an exception if the key is absent from the tree. Insert is given a key value pair and makes sure that that key is in the tree. And erase is given a key and makes sure that that key is absent from the tree. It removes it out of the tree if necessary. Let's review what the height situation is in binary search trees. Remember that the variable n usually means the number of elements in a data structure. In the case of our binary search tree that holds key value pairs, n is the number of key value pairs in the tree. H is the variable that's usually used for height, h for height, and it's the height of the tree. And the way that heights are defined is a leaf has height 0, and a parent node has height equal to 1 plus the maximum of the height of its two children. And the worst case binary search tree, meaning the highest possible binary search tree, has height n minus 1. Basically, every single node only has one child, and so the height stacks up basically to be equal n. It's n minus 1 because of the off by 1 aspect of indexing from 0 with the heights, but basically it's just as high as the number of nodes. And so we would say that's big O of n. We just drop the minus 1 out of the big O notation. Linear height in the worst case. So our binary search tree does not do anything to prevent that from happening. So we have to assume in the worst case that if an operation takes a big O of h time, meaning time proportional to the height of the tree, that's the same as big O of n time. That said, we are going to try to keep track of whether operations take big O of h time proportional to the height or big O of n time proportional to the number of nodes, because soon we're going to see that there are variations on binary search trees that are called self-balancing, and they make sure that the height is big O of log n. So we want to keep straight the difference between n, the number of elements, and h, the height of the tree. Now we're going to go through each of these operations one at a time. The first operation is the constructor of the tree that creates an empty binary search tree. All it has to do is initialize the root pointer to null and initialize the size to 0, and that's it. So those are two constant time operations, and the constructor takes constant time, big O of 1. Now contains key. So contains key does a binary search tree search. We've analyzed that already. Remember that the way that a binary search tree search works is you start at the root, and then there's a loop that keeps going deeper and deeper in the tree until the search is over, because we either found what we wanted or reached a null pointer and we know that the key is absent. So every loop iteration goes down one level deeper from the root, and so the maximum number of loop iterations is h, the height of the tree. That loop spends constant time on each level. It's just that if statement that says if the key is equal to what I'm looking for, stop the loop. If the key in this node is less, then go one way, otherwise go the other way. So it's constant time per loop iteration. Contains key takes big O of h time, and in a plain binary search tree, big O of h is the same as big O of n. Okay, find is given a key, and it basically does the same thing as contains. There's just a difference in the way the output is presented to the caller. Contains key always returns a Boolean true false. What find does is it returns a reference to a pair containing the key or throws an exception if that key does not exist. So that doesn't change the runtime of this algorithm. Find key does a binary search tree search, and search takes big O of h time. Okay, now we're going to get into the insert operation, then we're going to do the erase operation, and these involve helper functions. Just briefly review how insert works. So insert is given a pair that we want to make sure is in the tree. If the tree already contains that pair, then we return false and do nothing. Otherwise, we call this InsertNode helper function that puts the pair into the tree, size plus plus return true. And then what InsertNode does is it's given a pair that's definitely not in the tree already, and we search downward to find the place where that node would be if it were in the tree, and then create a node there and update the parent and root pointers as necessary. So in order to know the runtime of insert, we have to know the runtime of contains and InsertNode. We just worked out contains. We need to analyze InsertNode first, and then we can say what the total runtime of insert is. So InsertNode has that loop that goes from the root at the top of the tree down to a leaf. It spends constant time per level, and therefore it takes big O of h time, just like the contains or the find operation. It's the same kind of loop. Start at the root and work your way down. So the maximum number of iterations is the height, so big O of h time. Creating the new child is constant time, and updating those parents pointers is constant time in those if statements. There's no loops in any of that. So InsertNode takes a total of big O of h time for the loop to get from the top to the bottom, constant time to create a new child node, and constant time to update the pointers. So that's big O of h time for InsertNode. Now we can analyze insert pair, and it's pretty easy. The contains operation takes big O of h time. That was earlier in this video. And InsertNode takes big O of h time. That was the previous slide. Size plus plus is constant time. Return statement is constant time. So altogether, you've got big O of h time for the contains plus big O of h time for InsertNode, 2 constant time steps. So big O of h time is the bottleneck. Now we're going to get into the removal process, and we have to do the same kind of top-down, bottom-up analysis. Ultimately, we want to analyze the erase operation, but erase calls EraseNode, and EraseNode calls other operations. So what we need to do is work our way up from the bottom in kind of a LIFO order and start with the last function in the chain, analyze that, then we can work our way up. So the most low-level helper function that does not call any other helper functions in the removal process is remove 0 or 1 child. And it's kind of complicated, but it's constant time. There's no loops or recursion anywhere in here. It's just a bunch of assignments and if statements. So every one of those steps is constant time. Remove 0 or 1 child is constant time. Okay, so now let's look at RemoveNode. RemoveNode calls remove 0 or 1 child, and we just worked out that remove 0 or 1 child is constant time. This has a big if. In the 0 or 1 child case, RemoveNode takes constant time. This if statement is a constant time step, and then remove 0 or 1 child is constant time. But in the 2 child case, there's this loop. So that would be the worst case scenario, is when the loop happens. The while loop takes big O of h time. This starts at u. U is a pointer to a node, and finds a successor by going right and then left as far as we can. So the maximum number of iterations of this while loop is h, the height of the tree. So this while loop is big O of h. All of the other stuff in this case is constant time. This if statement is constant to assign w. Copying the contents is constant time, and we said remove 0 or 1 child is constant time. So RemoveNode is constant time plus the big O of h while loop plus constant time. It's big O of h total time for RemoveNode. Now we can analyze EraseNode that calls FindNode and RemoveNode. FindNode does another one of these searches starting at the root and working its way down. FindNode takes big O of h time. RemoveNode we just analyzed on the previous slide, and it takes big O of h time. So EraseNode takes big O of h for FindNode plus big O of h for RemoveNode is big O of h total time. And finally, we can analyze the overall erase function. The contains operation takes big O of h time. From earlier in this slide deck, EraseNode takes big O of h time. That was the previous slide. And the other stuff are constant time, science minus minus, and return. So altogether, we've got big O of h plus big O of h plus constant time makes big O of h total time. Okay, so let's summarize all of this. The constructor that initializes an empty binary search tree takes constant time. All of the other operations take big O of h time, proportional to the height of the tree. That's contains that takes a key and tells you whether it's present. Find that takes a key and gives you a reference to the pair containing that key or throws an exception if there is no such pair. Insert takes a pair and guarantees that it's in the tree. And erase takes a key and guarantees that the key is not in the tree. So they all take big O of h time, and in our plain unbalanced binary search tree, that could be as much as big O of n. So right now, this doesn't look very good for the binary search tree, we have to say. We developed earlier the association list that was just a vector of pairs, and it took linear time for all of these operations and was quite a bit simpler, I have to say. So right now, this doesn't look great. We created this binary search tree that's quite a bit more complicated than the association list, and it still takes linear time. However, there's a big innovation we can make to the binary search tree, which is to make sure that the height is less. There are self-balancing binary search trees that guarantee that the height is always log of n. And if we make that change and the height is log of n, then all of these operations will immediately become big O of log n, and log n is a lot faster than big O of n. So that's what we're going to get into next.